Hey guys, today we're going to go over our final exam review for second semester, so the spring final exam review. Let's start off with electrostatics. What parts of an atom carry charge? What particles can move from an atom to change the charge of an object? Electrons, protons, or neutrons? Why can that particle move? Okay, well, what parts of an atom carry charge? Well, if you look back in our notes, we'll actually see we kind of broke atoms down into multiple different parts. There's the nucleus, the center, and then there's the outside, which is the electrons. We have protons, we have neutrons, and we have electrons, as we can see listed right here. Now, for each of these, they have some charge. Protons are positive, electrons are negative, and neutrons, well, really, they don't carry a charge. Now, what particle can move from an atom to change the charge? That is the electron. Electrons are free to move. Why are they free to move? Well, if we think about the structure of an atom, we really have this nucleus, which is all in the center, and we have these neutrons and protons. They're all bundled up in the center. This is why I'm drawing all these bundles. These are all protons and neutrons, all tightly packed together. On the outside, we have electrons. You can kind of think of these electrons as almost orbiting this center point. So these electrons, they're orbiting this central nucleus, and these are all negatively charged. So inside that blue, that's our positive charged protons and our neutrons, which have no charge. Those electrons, since they're on the outer shell of the atom, if you will, they are able to move, whereas those protons, held in the center, they cannot move. Number 2, while insulated from the ground, you touch a Van de Graaff. Ooh, my bad. Just want to make sure we're still recording. While insulated from the ground, you touch a Van de Graaff generator. Why did your hair stand up? Explain in detail. Okay, so when we first turn on a Van de Graaff generator, we are saying that that Van de Graaff generator is bringing all of the negative charges to the top. So if we draw out a little Van de Graaff generator right up here, Van de Graaff generator is essentially depositing a bunch of negatives up here. There's still positives. It's just that since there's extra negatives, it becomes negatively charged. When you are touching the Van de Graaff generator, those negative charges, they're repelling each other. They don't just want to stay on that conducting sphere on top of the Van de Graaff generator. They want to distribute because the electrons, like charges, repel. The electrons are repelling each other. So when you touch the Van de Graaff generator, let's just say you take your finger, you touch the Van de Graaff generator, well, now electrons are going to distribute themselves along you in particular. All right. Like I was saying, those negative charges, those electrons are repelling each other. So that means they're going to evenly distribute themselves throughout your body. That includes your hair. So all of your hair becomes negatively charged. If all of your hair is negatively charged, well, like charges repel, all of your hair is going to repel all your other hair. So they're going to get as far away from each other as possible. Your strands of hair will. Number 3. Explain using this fact the process to get a charged balloon to stick to a neutrally charged wall. All right. So if you look at this PET simulation, this is going to be the balloon sticking to the wall. We'll launch this. What we can do is right now we have a neutral balloon. We can stick it to the wall, but it will work a whole lot better if we do a little bit of charging by friction, right? We rub this balloon on this sweater. We can use the triboelectric series to determine what is going to be more electron loving, what is going to pick up those electrons, and what is going to donate those electrons. We see, okay, our balloon, that rubber, it's more electron loving. It picks up the electrons. This is how you determine what is going to become positive, what's going to become negative when you're charging by friction. If we bring this near, and watch what's happening, when I bring this near the wall, those negative charges, those electrons, they're rearranging themselves in the wall. Now, why is this happening? We have this negative balloon. As we bring it closer, the force, it's really inversely proportional to the distance squared. So as that distance, this negative balloon is from the wall changes as I bring the balloon closer, that force is going to increase. It pushes the electrons further away. Now, this sticks. The wall is neutral, so why is the balloon attracted to a neutral object? This is polarization. We have a charged object, our negatively charged balloon. When we bring that negative object near the neutral object, that object arranges itself internally in such a way that those negative charges, the ones that are providing that repelling force, they are as far away as possible. The positives, in this case the ones that are providing that attractive force, they're as close as possible. Since the ones that are farther away will have less force than the ones closer, that attractive force is going to win. This is always the case with polarization. A neutral object is attracted to a charged object because of the polarization of those charges within that neutral object. Again, to view the polarization, see how this is just a neutral wall. We move the negative balloon near, that pushes the negative charges further away. Since they're further away, they push back on the balloon less. Then those positive charges pull on the balloon. So we get, overall, this force of attraction. To note, I'm not charging the wall here. The wall still has the same number of protons and electrons. It's still neutral. It's just been polarized. All right. Let's look at this physics classroom link to explain how a charged rod always attracts a neutral metal can. This is one that we use in class. And it's really going to be more polarization. Let's show our charges. If we bring in a glass rod, notice how everything's evenly distributed. This is a perfectly neutral aluminum can. When we introduce our glass rod, we're not charging the aluminum can. It has the same number of protons and electrons as it started with, but we can cause it to move. It's always going to be attracted to this glass rod. The glass rod's positive. It's attracted to the glass rod. Let's swap to the rubber rod. Well, the rubber rod's negative. Does this mean it'll be repelled? No. It's still attracted. Polarization always creates attraction. If you have a neutral object and a charged object, they will always attract each other because the charges inside that neutral object rearrange themselves. They rearrange themselves so that the charges getting repelled are farther away, the charges getting attracted are closer, and this difference in distance is what causes that attraction. Here, let's switch to our positive. The negatives, the ones that are attracted, are closer. The positives, the ones that are repelled, are on average further away. So overall, since that attractive force, it's closer, it's stronger, it's going to win out. Let's head back into our document. Explain the difference between a conductor and an insulator. Well, in a conductor, the electrons are free to move. In an insulator, the electrons are not free to move. They are locked mostly in place. Really, if you think about the conductor, we like to use in class this analogy that a conductor is like a sea of charges. Your positives are locked in place, but you have an electron sea. They're just all over the place. Whereas for an insulator is much more like a tightly knit group, where you have a group of a proton and electron, and they're bound together. So they could rearrange themselves, but they're always going to be bound together. Whereas in a conductor, the electrons are not bound to any one specific atom. Right, let's take a look at this link. What are the methods of charging? Here, if we walk through, let's see, name that charge. Okay. If we flip back. Alright, so there's 3 methods of charging, and we'll talk about them. The first is friction. This is when you take your rabbit fur and you take your, say, rubber rod, and you rub them together. This is charging by friction. Anytime things rub together, say you're doing laundry, you pull two pieces of clothing apart, you hear that static. This is charging by friction. It's just charging really by rubbing objects together. It follows the triboelectric series. The ones that are more electron-loving will take the charge. Our next method of charging is conduction. This always involves two conductors, and they simply touch. If you have a positively charged conductor and a neutral conductor, after they touch, they will both be positively charged. The one charged conductor will share its charge with the other. How does this actually happen? Well, imagine a neutral conductor and a negatively charged conductor. That negatively charged conductor has an excess of electrons. When it touches the neutral conductor, it will share those excess electrons. Now, they'll both have an excess of electrons. Our last type of charging is induction. Now, induction is one of the most complicated methods of charging. This is because you're inducing the charge to move. Now, there's many steps here. Let's say we have two neutral metal spheres. Let's say they each have 4 protons, 4 electrons. So they're both neutral. Okay. If we introduce, say, a negatively charged object, this has just a ton of electrons. Maybe still 1 or 2 protons, but it's a negative overall. We bring that negatively charged object near our first conducting sphere. Let's call this sphere 1, sphere 2. If we bring it near sphere 1, well, now what happens? Well, all of those negative charges are going to be repelled. Do our very best to draw this in. Those negative charges, they get pushed as far away as possible. Then, now, these negative charges are being repelled. If we bring sphere 2 in contact right here with sphere 1, now those negative charges can jump over. Those negative charges, they hop on over. So, if we take this negative charge, they want to get as far away as possible. Let's draw back in our circle. Now those negative charges, they're all over here, as far away as possible. This then lets us, if we remove object 2 from contact with object 1, and we remove our negatively charged object, well now, suddenly, object 1 is positively charged, and object 2 is negatively charged. Alright. For charging by friction, you are always going to get 2 oppositely charged objects. Charging by conduction, you will always get 2 like charged conductors. And then charging by induction, it really depends. Depends on if the objects start out with a charge, if they start out neutral, how many charges they have. So it depends on the situation. Number 7, Coulomb's law. This is an equation saying that the force on a charged object from another charged object follows the equation K Q1 Q2 over R squared. Now K is just a Coulomb's constant. It's part of Coulomb's law. Q1 and Q2 are the amount of charge on the first and second object respectively, and R is the distance the objects are apart. We have all of these givens. I'm going to leave off our units K is 9 times 10 to the ninth, so it's a really, really large number. Q1, well, charge on object 1 is 6 NC. What is NC? NC is nanocoulombs. So this is 6 times 10 to the negative ninth. Nano means times 10 to the negative ninth. So 6 nanocoulombs is 6 times 10 to the negative ninth coulombs. Then 4 nanocoulombs for object 2. 4 times 10 to the negative ninth. Again, that's just from our prefix. Nano is times 10 to the negative ninth. Then r squared. Well, r is the distance they are apart. We see they are 0.1 centimeters apart. There is 100 centimeters in 1 meter. So this means we want to convert from centimeters to meters to plug this in. 0.1 centimeters is 0.001 meters. Don't forget, we want to square this. And if we go ahead and we type this all into our calculator, we'll go ahead and get our answer. Let's do that. So we started off, let's clear this out. 9 times 10 to the ninth times our 6 times 10 to the negative ninth, that's 6 nanocoulombs, times 4 nanocoulombs, divided by 0.001. Now, that 0.001 is squared. Instead of inserting the square, I'm just going to divide by that same number twice. This is actually the exact same thing as dividing by 0.001 squared. When I'm doing all of my work with scientific notation on calculators, I like to go step by step. Do one thing, then the next, then the next. This guarantees I'm not plugging in anything wrong because I can manually control the order of operations. So we get our answer, the force, 0.216 newtons. That's our unit for force, and we know these are both positively charged, so it is going to repel, like charges repel. All right, let's keep rolling on to momentum. Impulse. Impulse is simply a change in momentum, delta P. Delta is change, P is momentum. This is a change in momentum. That is the most simple definition. If something changes its momentum, it must have experienced an impulse, since impulse is a change in momentum. Now, we also know that that change in momentum, the impulse, is equal to the force that object experiences over some amount of time. These are all equivalent. Impulse is a change in momentum, which is a force felt over some time. Momentum is simply mass in motion. Now, that's a nice snappy way to say it. What does that really mean? Momentum, P, is equal to m times v. It is an object's mass times its velocity. So if an object has no velocity, its velocity is 0, it cannot have momentum. A huge building, the Eiffel Tower, it has a ton of mass, but it doesn't have momentum because it's not moving. To have momentum, the object must have mass, and it must be moving. With these definitions, let's try some math. A 750 kilogram object moves at 25 meters per second. Okay, well, momentum is mass in motion. Momentum is P equals mv. Let's go ahead and plug this in. The m is the 750 kilograms. The v is our 25 meters per second. If we go ahead and we multiply these together, and I'm just going to do this on my little calculator off to the side here, 750 times 25, we get, for momentum, 18,750. Now, what should our units be? Well, all we're doing is we're multiplying mass times velocity. So, our units should do the same. Take units of mass, multiply them by units of velocity, and we have our units of momentum. Momentum is measured in kilogram meters per second. B. The object slows to 15 meters per second. Calculate the impulse. Well, impulse is a change in momentum, right? We know this. we're looking for delta p. We know delta p is equal to force times time. That's well and good, but we don't have a force. We don't have a time. How are we going to solve this? Well, since impulse is a change in momentum, if we can find the change in momentum, we know the impulse. There's an equation for this. Delta p is just p final minus p initial. Find your initial momentum, find your final momentum, plug them in, and solve. Up here, what we have right up here, this is your initial momentum. You were initially going 25 meters per second. So we plug that in for pi. Pf, well, in the end, we're going 15 meters per second. This is your final. So if we plug this all in, right, delta p is equal to Pf is the mass of the object, 750, times its final velocity, that 15 meters per second. Then we're subtracting our answer from above that we got for that initial momentum, 18,750. We'll get our answer. 750 times 15 gives us 11,250 minus 18,750. This gives us an answer of negative 7,500. What's our units? Well, it's still momentum, so kilogram meters per second. Why is it negative? Well, we had an object, 750 kilograms. It was moving pretty fast, 25 meters per second. It slowed down to 15 meters per second. So that means it should have a negative change in momentum. It lost momentum. That change in momentum should be negative since it decreased. C. It took 7 seconds for the object to slow from 25 meters per second to 15 meters per second. Calculate the force that must have been applied. Here, a big trick in momentum is knowing these equations that we have written right here. Knowing how to relate a change in momentum to a force times time. Oftentimes, you're given enough to use one half of the equation. You're given masses and velocities. Sometimes you're given forces and times. Know what to plug in, what equation to use based on what you're given. Here, we're given time. This is a huge giveaway. If we're given time and momentum, we're gonna most likely need to use force times time. So it took 7 seconds for the object to slow from 25 meters per second to 15 meters per second. Calculate the force that must have been applied. We just found that change in momentum. I'll write this out in black. Change in momentum was negative 7,500 kg meters per second. Well, we also know change in momentum is force times time. Plug in that negative 7,500. This must be equal to force times time. If we plug in our 7 seconds, now we're really getting somewhere. Divide by 7, and we find that that force must be negative 1,071.4. Now, why the negative? This negative just means that that force is applied in the negative direction. This makes sense. A force is applied to us in the negative direction, we slowed down. Awesome. Everything makes sense. Alright, number 11. Describe using this physics classroom link how each of the following keep drivers safe in a car crash. Make sure to use terms like force, time, impulse, and momentum. Let's take a look at our link. If you hop in here, this is an egg drop interactive, so you can mess around with an egg drop, seeing what kind of egg drop you get, right? You can mess around with your egg size, drop height, and landing surface. If we drop a small egg from 1 meter onto a hard floor, run the trial, drop the egg, and we see what happens. What you'll find is, well, the egg breaks. How could we say that? If we change our conditions, right, we have a hard floor. That's probably not the best for the egg to land on, right? If we had it land on maybe a pillow, maybe it still survives. Why is that the case? Well, this really relates to car crashes and car safety. When you experience some collision, Let's say here's a wall, thick, sturdy wall, and you're driving in a car. Here's our lovely car, and it is going some velocity. It has some mass m. It has some momentum, right? Momentum of this car, this vehicle, is mass times velocity. That's a lot. It can have a lot of momentum. Cars have a lot of mass. They generally go pretty fast. What happens when it hits the wall? Well, it comes to a complete stop. It loses all of its momentum. If it loses all of its momentum, it changed its momentum by the same amount. If we look at our change in momentum equation, final minus initial, well, the final momentum here is 0. Comes to a stop. The initial momentum is just the mass of the car times the velocity of the car. It'll always be the same, assuming it's the same car going the same speed. So you get this same change in momentum. What do crumple zones, seatbelts, and airbags have to do with any of this? Well, they say that using our laws of momentum, even for the same change in momentum, the same car going the same speed, coming to a stop, the passengers can experience a drastically different force based on their safety devices. Why is this the case? Well, because delta P, that impulse, is also equal to force times time. So if you have a certain amount of change in momentum, of impulse, if you come to a stop really quickly, you minimize that time, you're going to feel a huge force. If you come to a stop over a long period of time, that force is going to be minimized. Let's view this another way. If you have the same size change in momentum, and here I'm using literal size, I'm drawing out these two delta P's to the left. They're the same size change in momentum. We know change in momentum is force times time. You can get the same value in an equation if you plug in a massive force in a little teeny time. Or if you apply a little teeny force for a really long time. This is why we have crumple zones. Cars are designed to crumple because it takes time for the car to crumple. In that time, the car is applying less force on you, so you don't immediately come to a stop. You come to a stop gradually over a longer period of time. That's what seatbelts are meant to do as well, right? Seatbelts, they help you come to a stop at not just one time. They're actually designed to give just a little bit during crashes so that you're not immediately stopping. You're not hitting a brick wall. Well, your car is, but you yourself are not. You're hitting the seatbelt, which gives a little bit. It's just like when you drop an egg onto a pillow. Dropping an egg from a height onto a hard floor versus dropping an egg from that same height onto a pillow gives you vastly different results. All right. So, where were we? Soccer ball travels at 10 meters per second in the air when it hits the goalie's hands. Soccer ball is in contact with the goalie for 0.01 seconds and rebounds from the goalie with a speed of 5 meters per second. The mass of the ball is 0.4 kilograms. Calculate the force the goalie applies on the soccer ball. Determine the force the ball applies to the goalie. Okay. So, big thing with momentum. Draw pictures. Pictures help so much. You start out. There's a soccer ball. It's traveling 10 meters per second. It hits the goalie's hands. I'm not going to draw hands. I'm not an artist. I'm just going to draw a wall. That's the wall. It represents the goalie's hands. Then, it's in contact with the goalie for 0.01 seconds. And then it rebounds. This is a huge keyword in momentum. This means it's changing direction. It has gone from 10 meters per second in the positive direction to the right to now 5 meters per second in that negative direction to the left. What this means, it went from positive momentum to a negative momentum. So, this is our initial. It was initially moving to the right. In our final, it is moving to the left. Let's use our equation. Change in momentum, that's equal to the impulse. Change in momentum is final momentum minus initial momentum. Our final, again, momentum is always m times v. So, rewriting delta p equals pf minus pi, replace pf and pi with mv. The final momentum is the mass times the final velocity. The initial momentum is the mass times the initial velocity. If we plug in here delta p, the final momentum is just the mass of the soccer ball, 0.4 kilograms, times the velocity of the soccer ball, -5. Now, of course, we subtract the initial momentum. It still has a mass of 0.4, and it now has a velocity to the right, +10. Do our math and get our answer. 0.4 times 5, and that's a -5, so this gives us -2 minus 0.4 times 10 is just going to give you 4. Now again, -2 minus 4, well, of course, our answer there is -6. What's our unit? Well, it's momentum, so kilogram meters per second. -6 kilogram meters per second for our change in momentum. But that's not quite the end. We have to keep going. We know change in momentum is also equal to force times time. So once we figured out the impulse, over here, this is the impulse. This is the change in momentum. Now we can calculate the force. Plug in that -6 for our change in momentum. We're solving for the force. Plug in that time. The goalie is touching the ball for 0.01 seconds. Now we go ahead, we do a little bit of division, and we get our answer for the force. The force applied would be -600 newtons. Again, why the negative? It's because it was moving in the positive direction. It ends up moving in the negative direction. We need a negative force to do that, a force in the negative direction. Can something very small, like a tennis ball, ever have more momentum than something very large, like a car? Absolutely. If you have a tennis ball, and it is just flying at 500 meters per second. Now, I don't know who launched that tennis ball so fast. It is certainly going to have more momentum than a car that is moving extraordinarily slowly, like 0.00001 meter per second. Or, to be even more dramatic, what if the car wasn't moving? What if you're looking at a building? What if you're looking at Prospect High School? Prospect High School has a ton of mass, but it doesn't move. It's stationary. It has no momentum. A tennis ball, even just a lightly tossed tennis ball, is going to have more momentum than Prospect High School. An ant crawling on the sidewalk has more momentum than Prospect High School, because if something doesn't move, it has no momentum. A 30-kilogram cart is traveling at 2.7 meters per second. Calculate momentum. Very straightforward question. P equals mv. Plug in your mass of 30. Plug in your velocity 2.7. Do your math. Bing, bang, boom. What's our answer here? 81. Our units, it's momentum. Kilogram meters per second. To increase the change of momentum on a ball, if you were hitting it with a bat, what two factors can you increase? Well, let's look at change of momentum. Change of momentum, we know it's equal to force times time. These are our two factors. You can increase the force. You can swing harder, hit the bat with greater force. Or you can increase the time you are in contact with the ball. How do you do that? You follow through. This is why in almost every sport where you want to hit something hard, you want to follow through. You're maximizing the time that you are in contact with the ball, and that literally increases how much the ball changes momentum. You literally end up with the ball moving faster if you follow through, just because of that minute change in how long the bat or the tennis racket or the golf club is in contact with the ball or the puck or whatever it is you're hitting. Ginger the dog has a mass of 30 kilograms. She is standing still on a motionless 124-kilogram boat. Ginger sees a duck in the water and jumps forward off the boat, moving at 3.2 meters per second. Okay, this is the start of going over collision problems. These are your explosions. These are your inelastic collisions. These are your elastic collisions. Again, I really, really, really recommend drawing pictures for any type of momentum problem. We'll start with our initial state, right? We have Ginger the dog standing on a boat. Here's our boat, and we'll call that our dog. Yes, lovely. Ginger standing still on this boat. Ginger sees a duck, jumps forward off of the boat. So what do we end up with? Well, if they're not moving, they're both not moving, both at a velocity of 0, Ginger leaps forward So now it has some positive velocity. Well, what happens to the boat? It must be moving backwards. How do we get there? Well, let's start with part A. Determine the initial momentum of the boat-dog system. Well, initial momentum is just the mass of the system multiplied by the velocity the system's moving at. Well, the boat's not moving. We have no velocity. If we have no velocity, we have no momentum. So that initial momentum of the system is 0 kilogram meters per second. We know because of the law of conservation of momentum. It's a mouthful. Can't spell. Conservation of momentum. That the initial momentum of a system must equal the final momentum of that same system. Our system is the dog in the boat, so they started with no momentum, they must end with no momentum. So our final momentum of the system is still 0 kilogram meters per second. Calculate the velocity of the boat immediately after Ginger jumps. How I always set up my problems is I separate out our equation. We say that the initial momentum equals the final momentum. And I split this line down the middle right here because on our left-hand side is initial, before the collision or the explosion. Right-hand side is after. So initial, before that explosion. Treat the dog and the boat as one object. Combine their masses. We would combine the mass of the pup plus the mass of the boat times their velocity, whatever their initial velocity is. That must be equal to the final momentum. Now, they're separate. They're no longer moving together. Treat them as separate objects. This is the mass of the pup times the velocity of the pup after the collision or explosion in this case, plus the mass of the boat times the velocity of the boat. How do we get here? It's just conservation of momentum. P initial equals P final. Initial total momentum equals final total momentum. Without all our subscripts, what does this really originate from? It originates from m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And this is just using the law of conservation of momentum. If we plug in all of our values, well, we know on our left-hand side, we get 0, right? They're not moving. They have no momentum. What is the mass of our pup? 30 kilograms. And what velocity do they have after the explosion? Well, they're moving 3.2 meters per second. The mass of the boat is 124. Solve for this velocity. We go ahead, do our multiplication. 30 times 3.2 right here, that gives us 96. Move it over, subtract it from both sides. We get negative 96 is equal to 124 times the velocity of that boat prime after the collision. Divide both sides by 124, and we find, okay, our velocity of the boat after the collision is negative 0.77. Does this negative answer make sense? Well, the dog jumped forward, the boat must go backwards. Yes, that makes sense. Let's continue rolling. Number 17, 125 kilogram tackler moving 4 meters per second meets head on with a 95 kilogram halfback moving towards the tackler at 6.5 meters per second. Calculate their mutual velocity after collide and stick together. Okay. Well, notice a couple of keywords. They are colliding head on. That's important. They're also colliding and sticking together. If we draw out a little picture, and I'm just going to treat them as squares. That way, it makes it a little bit easier for me to label everything. Here is our 125 kilogram tackler. They are moving 4 meters per second. They're meeting head on. That means the halfback is moving the opposite way. They're moving 6.5 meters per second. And in fact, this would be negative since they're moving the opposite direction to the left. Now, what does this look like after our collision? We've drawn a picture for before. Let's draw a picture for after. They collide, they stick together. So that means we have our 125-pound tackler and our 95, oh, not pound, kilograms, our 95-kilogram halfback. They stick together. We don't know what direction they're going to move in, but we know they stick together. What does this let us do? Well, we can use our big equation over here, our law of conservation of momentum equation. But what we want to do is customize it for our very own problem. Here, we do start with m1 v1 plus m2 v2. But on our right-hand side, don't separate your two terms. Treat these tacklers, these football players, as one object. When they collide and stick together, they must have the same velocity. So let's simplify that. 2, really it's just m1 plus m2. Treat it as one mass, just combining them, adding them together, traveling at some final velocity. If we plug everything in, well, we have 125 kilograms times 4 meters per second plus 95 kilograms times negative 0.65 meters per second. Make sure you remember that negative. That is absolutely crucial. Is equal to, well, 125 plus 95, and that quantity times our velocity. If we go ahead and do all of this in our calculator, we should come away with that velocity negative 0.53 meters per second. A 0.04 kilogram dart is thrown at 35 meters per second. I'm going to draw as we go. Here's our dart. It is 0.04 kilograms. It is thrown 35 meters per second into a stationary block of wood. Now here, having the arrows is a little confusing. So let's maybe make this thicker. So this is our dart. And it's traveling to the right. It's going to hit this block of wood. It is stationary. So there you go, so it's not moving. It bounces backwards off of the block. Again, this is 2 kilograms. It is not moving. Afterwards, well, the block, we can surmise, is moving to the right with some velocity. And we know that dart is now moving to the left at negative 12 meters per second. And let's do our equation. Here we are going to use m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. We're not combining any masses because they're never hitting and sticking. They don't start together. They don't end up together. They're apart the whole time. So let's plug everything in. 0.04 for m1 times our 35 plus 2 times 0. Well, this just gives us 0. The mass of the dart, again, it's that 0.04 times negative 12 plus 2 times this velocity. That's what we're solving for. Our right-hand side, 0.04 times 35 gives us 1.4. Our right-hand side, 0.04 times negative 12 will give us negative 0.48 plus 2 v2 prime. Move our negative 0.48 over. We do this by just adding 0.48 to both sides, of course. This will cancel on the right-hand side. So we get 1.4 plus 0.48. And let's do this in pink. Now we end up with 1.88 is equal to 2 v2 prime. Divide both sides by 2. And we get that velocity, v2 prime, to be 0.94 meters per second. Alright, looking at circuits. Remember that when we plug something into an outlet, you can assume that the outlet provides 120 volts. Number 19, home circuit has a fuse labeled 20 amps, which appliances, as many as you can safely be plugged in without blowing the circuit. Choose from 60-watt light bulb, 1700-watt hairdryer, 200-watt television, a 2500-watt microwave, a 2000-watt dryer, and a 5-watt phone charger. Okay, well, so we want to try to plug in as many as possible without blowing the circuit. How are we going to do this? Well, we have some equations here. Notably, we have that power is current times voltage. This is what we're really going to use because we can solve for the current drawn by an appliance if we have the power and we have the voltage. If we do that, now, well, we have the voltage, right? Voltage is given, we plug it in. We're assuming it's 120 volts. The power rating, then, is just the watts. So, let's do this calculation. Every time, we're just going to be taking, if we rearrange to solve for the current, power divided by voltage is going to give us the current. So, let's do this for the light bulb. We take our 60 watts, divide by our 120 volts. We find it draws 0.5 amps. Okay, now we move on to the hairdryer. Same calculation, right? The power, 1700, divided by that 120 volts. This one will draw 14.16 amps. That's a ton. Then, if we keep rolling, let's look at our TV. 200 watts divided by 120 volts, 1.6 amps. What about our 2500 watt microwave divided by 120? This is 20.8 amps. Okay, so that's already too much. That would blow the fuse. We also have a 2000 watt dryer. 2000 divided by 120. This is 16.7 amps. And what else do we have? We have a 5-watt phone charger. Charger. 5 divided by 120. This is only going to draw 0.042 amps. Okay. Which appliances can safely be plugged in without blowing the circuit? Well, we can plug in the charger, the TV, the hairdryer, the bulb. The dryer, we cannot plug in the microwave. If we want to plug them in at the same time, well, let's see. Let's start with our smallest. If we plug in just the charger, that's only 0.042. That's not much. What if we then plug in, and we'll just add, what if we plug in our bulb then? Adding 0.5, now at about 0.54 current. Let's add then our TV. Adding 1.6 current, right about 2. Let's add then our hairdryer. This is a big jump up. We're adding about 14.16. So we're still at 16, but now we cannot plug in the dryer or the microwave. That would put us over. 20, wire fuses placed in series with the appliance they are protecting. Well, fuses, they blow. They essentially get destroyed, and that breaks the circuit. It's no longer a closed circuit. It is an open circuit. Current cannot flow. A fuse is placed in series because if, just like in series, say we have 2 light bulbs in series. We have a light bulb right here, and then down here, we also have a light bulb here. What we find is that if you remove a light bulb, completely remove a light bulb, we remove this bottom light bulb, and you replace it with a wire, or really replace it with nothing, there's no light bulb there, now this circuit is broken. There's no longer a complete path. This means current cannot flow. So a fuse is placed in series because if that fuse blows, it literally leaves a gap in the circuit. Now no current can flow. If we did a parallel circuit, for instance, say we have a light bulb right here, and then we have a fuse along this wire. Well, if we left a little gap right here, if this is where our fuse was, there's a little gap. This gap doesn't prevent current from flowing. Current will still flow through our light bulb. It'll just keep going. But if we have in series, current's flowing, well, it can't actually flow because it's a broken circuit. Are switches wired in series or parallel with light bulbs? This is, again, very, very similar. They are wired in series most of the time with light bulbs. Now, of course, in our challenge, we saw some fancier light bulbs and fancier switches where you have maybe multiple switches that are in parallel with each other. But for our basic switches, in order for a switch to turn off a light, you need to be wired in series. It works exactly like the pictures that I just drew. If you put your switch in to fill this little gap right here, if your switch is here, closing that switch, opening that switch, now of course if you closed it, it'd be a short circuit. That's not really going to be very effective. You don't want a short circuit. Whereas if you add in your switch right here, now, if you close it, now there's a full path, the light comes on. If you open it, that's like turning the light off. Now there's no longer a full loop. Current cannot flow. Discuss the following concepts. As you add light bulbs to a strand of lights wired in series, what happens to the current? So if we are doing series, and I'm actually going to pull up a little bit of a different video, or not video, but a simulation here. Let's look at our circuit constructor simulation that I already have right here. If we refresh our page, should come right up. Excellent. Let's start building. So in series, right, we have one battery, and we have one light bulb. Nice and simple. Let's bring in our another wire, and one more wire for good measure. We can measure the current. What happens if we add, again, this is the same current, it's uniform, it's in series, current is the same everywhere, still 0.9 no matter where I look. What happens if we disconnect these wires, and we then connect in a second light bulb? Now, current's still uniform everywhere, but it has decreased. It has decreased. So if we look back, as you add light bulbs to a strand of lights wired in series, what happens to the current? Well, through one bulb, it decreases. You have increased the overall resistance of the circuit using V equals IR. Voltage is determined by the battery. You've increased the resistance, the current must decrease. Through the battery, it's still going to decrease. Current is the same everywhere in a series circuit, so the current through the battery is also decreasing. As you add light bulbs to a strand of lights wired in parallel, what happens to the current? Well, let's take a little look. Here, let's go right back. We'll delete this. We'll rewire these. We see, okay, we have our 0.9 everywhere. Now, let's wire in parallel. And what we'll really do that is we will add another, let's bring some of this stuff up. Let's wire another light bulb, add in a wire. Bring this on down, bring this over, and connect. Okay. What have we done? Let's wire this, wire this. Let's build something a bit more simple. Here, we have our junction. It can split. It can go through this light bulb at the top, or our light bulb down here. This is in parallel. We noticed earlier, with one light bulb, current through each light bulb was 0.9. It's still 0.9, but the current through the battery has increased. Why is this the case? It's because when you add a light bulb in parallel, you're really decreasing the overall resistance. You're adding another path. Think about traffic on a highway. You're adding in a new path for that current or the traffic to flow. So the cars are going to move quicker when there's more paths. There's going to be less traffic. That resistance decreases because you've added another path. So, current in bulb stays the same. Current in battery increases. Number 24, draw wires in the figure to connect the components in series. Assume that each component has a 10 ohm resistance. What is the electric potential difference across each component? Well, we're wiring it in series, so let's do this in something blue. Right here, right here, right here, right here. Okay. If each one has the same resistance, well, we have 9 volts. We see that from our battery. It's right here. We're going to drop evenly. So the electric potential difference across each component would be 3 volts. We get that from our loop rule, where it says if we do one full loop, we have to drop all our voltage from the battery. So we drop 3, 3, and 3, leaving us with 0 right here before we pass through our battery and get brought back up to 9. What's the current for each component? Well, if we know the resistance is 10 ohms and the voltage is 3, we can use V equals IR, plug in R3, plug in R10, 3 divided by 10, we get 0.3 amps for current. Does the current through the light bulb increase, decrease, or stay the same if you switch the position of the light bulb and resistor? Well, light bulbs and resistors are really the same thing. A light bulb is a form of resistor, I should say. So you can just approximate this light bulb as a resistor. There would be no change. To put it simply, a light bulb is a form of resistor. So instead of this being a light bulb, just pretend that it is a resistor. Rewire the same 3 components in parallel. What is the electric potential difference across each component? So in parallel, we want options, right? We want from the positive terminal of the battery and the negative terminal of the battery to be connected everywhere. So here we have one path through our battery through that resistor. But we could also go, and let's try to not cross our wires too much. I don't want it to get too confusing. Here we've connected our light bulb to the positive. Now we need to connect it to the negative. So we have a full loop there. Excellent. And then we can come around this way, connect to our positive, and connect to our negative. These are all in parallel with each other. The electric potential difference across each component will be 9. This is, again, using the loop rule. For any one loop, you must drop all of your voltage. You could draw in a loop. That does not show up very well. What about, does it show up better? That should, not really. Okay, let's just do, right. If we go this way, this is one loop. This is also a loop. And this is a loop. You must drop all your voltage from the battery. You get 9. So if you're only coming across one resistor, one light bulb, you're going to drop all 9 volts there. We do our same. If we know that the resistance is 10 ohms, the voltage drop is 9 volts. V equals IR. 9 is equal to I times 10. So then here we get our current of, 9 divided by 10, 0.9 amps. How does the current or voltage, EPD, change if you switch the position of the bulb and a resistor? Excuse me. This would also not change. Again, light bulbs and resistors are, to a circuit, identical. The light bulb is really just a resistor. Some circuit puzzle practice. For these, I always want to encourage you, the 2 chief rules are loop rule and junction rule. When you do one full loop, you have dropped all your voltage from the battery, and current only ever splits at a junction. Current in equals current out. So with those, let's run through 26. Well, right off the bat, we have V equals IR. 2 times 4 gives us 8 voltage drop at number 1. We know, since this is in series, all the currents have to be the same. They're all 2 amps. There's no junction for it to split at. So 2 times 6 gives us 12 volts. 2 times 8 gives us 16 volts. If we add all of these up, 8 plus 12 plus 16, we get 36. Why are we able to do this? Well, it's a series circuit, sure, but let's dive a little deeper. If we draw one loop, the amount we drop in that loop must be the amount of the battery. We drop 8 here. We drop 12 here. We drop 16 here. Add those up, you get the voltage of the battery. Okay. Now, 36 divided by 2, 18 for our resistance. Let's move on to number 27. We have this parallel. Now, we don't have any voltages. We do have currents. What I like to do is I like to label my currents flowing through resistor 1. We have 1 amp. Flowing through resistor 2, we have 3 amps. Resistor 3, we have 2 amps. Well, current only ever changes at junctions. So over here, this is still 2 amps of current. When our 3 amps and 2 amps meet right here, they will join up, and we get 5 amps right here. When our 5 amps and 1 amps meet at this next junction, they'll combine, and we get 6 amps of current. There's no more junctions until we pass through the battery, so it just continues as 6 amps until it splits right here. And again, we get our 1 amp that goes down through R1, 5 amps that continues. It splits again at the junction, we get 3 amps down through R2, and we get our 2 amps that go through R3. So, what did that tell us? Well, the current through the battery is 6 amps. Again, V equals IR. Current times resistance, 3 times 12 is going to give us 36 for our voltage. Since this is in parallel, every one loop, you must drop the voltage of the battery. Let's go ahead and clear this out just so that we can draw in our loops a little bit clearer. Again, you, as you're following along, as you're drawing these, you can draw your current and loops on top of each other. I just want to make sure I'm totally clear. If we have one loop, you could go through and just go through R1. That's a loop. Or you could just go through R2. That works as a loop. Or you just do R3. Either way. Since we are dropping 36 at R2, and that is the only resistor we encounter, that is the only voltage drop, loop rule says the voltage drop across any one loop must equal the voltage across the battery. So, battery must be 36. If the battery is 36, well, you can also encounter only resistor 1 and drop 36 there. You could also go through resistor 3 and drop 36 there. And now we just have to take the voltage, divide by current, and we get our resistance. That gives us 36 ohms right here. That gives us 18 ohms right here, and 6 ohms right here. Now, do notice how this resistance is less than any of the individual resistances here. That's because when you add resistors in parallel, the overall resistance, that resistance of the battery, decreases. Let's keep rolling on. Make sure we're still recording. Excellent. Here, a complex circuit. It's important to recognize R3 and R4 are in series with each other. R1 and R2 are in series with each other. What do we know about series? Well, when circuit elements are in series, they have the same current. So, if 2 amps of current are flowing through R1, you can bet your bottom dollar 2 amps of current are flowing through R2. We know 5 amps are flowing through our battery, right here. So coming to this junction, we have 5 amps. At this junction, if 2 goes right, well, 5 comes in, 5 has to come out. 2 is going right. That means 3 is going up through here. That means passing through R3 is 3 amps. But R3 is in series with R4. There's no junction between them. So 3 amps must also pass through R4. And just like that, we have all of our currents. How do we get the rest of our voltages? Well, there we want to use our loop rule. Right? Junction rule is for current. Loop rule is for voltage. Using our loop rule, draw one loop. Doesn't matter what the loop is, as long as it goes from the positive terminal to the negative terminal. You must drop all the voltage from your battery. If we get 50 volts from our battery, we have to drop 50 along our path. If we drop 25 volts at R2, the only other place we can drop voltage is R1. So we must also drop 25 at R1. We can also draw in a loop going through this top path. If we drop 10 at R3, well then we must drop 40 at R4 so that they add up to 50 from the battery. And now we can just do all of our last calculations. V divided by I will give us R. We get 10. Here we get, 12 and a half. Here we get 12 and a half again. Here it is 3.3 about. And here, call this about 13.3. All right. Now we'll get into some power calculations. Again, gotta check I'm still recording. Perfect. 60-watt light bulb is used for 14 hours per day. Calculate the following if the electric company charges 10 cents per kilowatt hour. Well, if we start off, we're always gonna start off with the wattage. 60 watts for our light bulb. I like to set up my little train tracks right here. Whatever unit we have on top, whatever we want to cancel, needs to go on the opposite side. So if we have watts on our numerator, we need to put watts on our denominator so that it'll actually cancel. We want to turn watts into kilowatts. 1 kilowatt is 1,000 hours. Since we have watts and watts, these will cancel. We can even draw this in. Now we're in units of kilowatts. We want, again, cost per day. Let's keep going. After we do this kilowatt conversion, we're going to add in dollars per 1 kilowatt hour. The electric company charges 10 cents per kilowatt hour. That's a fraction. We can plug that in. What this will do, it cancels kilowatt hours with kilowatt hours. Now we're in dollars per hour. Okay, this is good. We're almost there. We just need one last thing to get the units we want. Let's get rid of hours. If hours is on the bottom, to get rid of it, we need to put it on the top. So we have some amount of hours per something. Well, I know there's 24 hours per 1 day, and day is actually what we want to end up with. This cancels hours, and we get to days. Stop your calculation at this point, because now our units are dollars per day. That's exactly what we want. Multiply across the top, divide across the bottom, and you'll get your answer. This is $0.84 per day. Why am I putting it over here? Well, I'm actually going to continue my work because now we're in cost per day. We can directly convert this to cost per month. Let's just take our days. Days is on the denominator. We need to cancel it. Put it on the numerator. Days cancel with days. Days over days, they cancel. Days per month. Well, there's 30 days in 1 month on average. So our days cancels. Then this is where we can stop for part B. Do the calculations. We should find. Oh, actually, let me add in a little correction here. I realized this for dollars per day should be 0.084. 0.084. Cost per month is $2.52 per month. And at the very end, let's turn months into years. Well, there's 12 months in 1 year. stuff, cancel out our months, and we have dollars per year. Do our calculations. That is $30.66 per every 1 year. Alright, on to wave, sound, and color. Number 30, the record player spins at 77 revolutions per minute. Calculate the frequency in hertz and calculate the period in seconds. Okay, so going over this, something I want to review is that for frequency, we know it's the inverse of the time period. 1 over the time period is the frequency, and time period is the inverse of the frequency. They're inverses of each other, right? But how do we actually get them when we don't have the other? Well, frequency is going to be cycles per second, and time period is going to be the inverse, right? So seconds per cycle. So here, well, record player spins 77 revolutions per minute. So frequency is, of course, cycles per second. So frequency are cycles, 77 revolutions, 77 cycles per 1 minute. So that's 60 seconds. 77 over 60. And if we just go ahead and do a little calculation, we'll get our answer, 1.28 hertz. Calculate the period. Well, now that we have the frequency, we can just take the inverse, right? Frequency is 1 over our, we're calculating period. Time period is 1 over frequency, so this would just be 1 over 1.28, and we'll get our answer. Now, of course, you could use the equation that we talked about, right? We get our answer here, 0.78. Our unit there would be seconds. This is how long it takes for one cycle, where frequency is how many cycles happen in a given second. Now, of course, we could have used our equation for time period right over here, seconds per cycle, and we get this same answer, but we just opted to use this inverse instead. In the wave below, the length from crest 1 to crest 3 is 12 meters. The vertical distance from the bottom of a trough to the peak of a crest is 1.5 meters. As the wave moves to the right, a student starts a stopwatch when crest 1 passes point P. He stops it when crest 3 reaches point P at 4 seconds. Okay. So length from crest number 1 to crest number 3. Let's just draw that in. This is 12 meters. Vertical distance from the bottom of a trough to the peak of a crest is 1.5 meters. Okay. So this is 1.5. Well, amplitude is from crest to equilibrium. So that'd be half of our 1.5. So that will give us 0.75 meters. What's the period? Well, if we look back at our equation for period, right, there's two ways to find it. We can take the inverse of the frequency, or we can take the seconds per every one cycle. We know it takes 4 seconds for crest number 3 to reach point P. Our cycles are whenever we have a crest past that point. So there's a cycle at 2 seconds when crest number 2 has moved all the way to where number 1 is, point P. It takes 4 seconds for number 3 to reach point P. So every cycle is happening once every 2 seconds. It's really time period. Again, this is going to be seconds per cycle. It's just going to be 2 seconds. And again, the reason we know that, it takes 4 seconds for crest number 3 to reach point P. That is 2 cycles, so we really have 4 seconds. 2 cycles happen. Why 2 cycles? Because crest number 2 passes that point, and crest number 3 passes that point. Those are our 2 cycles that are happening. For our wavelength, we've drawn our length. Wavelength is crest to crest, so 6, right? Just half of our 12 meters. And then velocity, well, velocity, we have a nice equation. Velocity is frequency times wavelength. We have the wavelength already at 6. We do not have the frequency, but we can find the frequency, right? Because frequency is just the inverse of our time period. So if our time period is 2 seconds, our frequency is 1/2 hertz, 0.5 hertz. Now go ahead and plug this in. We get 0.5 for that frequency. We get 6 for our wavelength. 0.5 times 6 is going to give us 3. It's a velocity, so units meters per second. Alright, describe how the Doppler effect changes sounds we hear or the colors we see. Well, Doppler effect is essentially saying the frequency of some sound, of some light color changes based on that object's motion relative to you. You've probably heard this with an ambulance or a fire truck. If they are blaring their siren and they are approaching you, you will hear a higher frequency. When they pass you, you will hear a lower frequency. Why is this? It's because as they're moving, let's check out our link. As the source of the waves is moving, the waves get emitted closer and closer and closer together. Just like this. For the person that the police car is heading towards, they hear that higher frequency because the waves literally bunch up and will pass the person's ear at a higher frequency. So you hear a higher pitch. It's the opposite if the source is moving away from you. You would hear a lower frequency, a lower pitch. And this actually works just like we mentioned in our study guide. This actually works for light as well. It's not just sound. Any type of wave experiences the Doppler effect. So light, that's actually how we're able to tell that distant galaxies are moving away from our own galaxies, because that light is shifted. Number 33. Let's double check we're still recording. Lovely. An electromagnetic wave has a wavelength of 3.25 times 10 to the negative 11th meters. Alright, determine the speed of this electromagnetic wave. So, something that might be confusing about this problem is that, what's an EM wave, right? EM just means electromagnetic, right? All electromagnetic waves is just a fancy way to say light. The speed of light is a constant. The speed of light is generally abbreviated by this variable c, where the speed of light, or c, is 3 times 10 to the 8th meters per second. That's the velocity of this wave. It doesn't matter if it's a radio wave, a microwave, visible light ray, ultraviolet, infrared, gamma ray. All light, all electromagnetic waves have the same velocity, and that is 3 times 10 to the 8th meters per second for all electromagnetic waves. Part B, calculate the frequency of this wave. Well, velocity is frequency times wavelength. We have the velocity, 3 times 10 to the 8th. We just are given the wavelength right up here. So we're solving for the frequency. Plug in our wavelength, 3.25 times 10 to the negative 11th. And now we just have to divide. When we do this division, we're going to end up getting 9.23 times 10 to the 18th hertz. That means that this wave oscillates 9 times 10 to the 18th times in a single second. That is so many times. Number 34. Explain the difference between pitch and loudness. What attribute of a sound do you change to change the pitch? Well, to change the pitch, that's all hinging on the frequency of the wave. High frequency is a high pitch, low frequency is low pitch. For loudness, this is all on amplitude. If you have a large amplitude, it's a loud sound. If you have a small amplitude, it is a softer, quieter sound. You repeat the standing wave lab with a 19-meter long rope. You create a 2-loop standing wave by shaking the rope 25 times in 16.3 seconds. Calculate the velocity of the wave in the rope. Okay. 2-loop standing wave. So let's draw that out really quick. Just so we have our picture. There's 2 loops. So in our middle, at this other node, this is what our standing wave pattern will look like. Okay. Now there's 2 loops. Each loop is 1/2 of a wavelength. So together, this is going to be a full 1 wavelength. We also know the length of this rope is 19 meters long. Since there's 3 nodes, there's 2 antinodes. Each antinode is half a wavelength. So like we just said, this is a full wavelength made on this rope. The rope's 19 meters long, so a full wavelength is 19 meters long. Calculate the velocity. Well, velocity is frequency times wavelength. We already have the wavelength. We just need the frequency. Frequency is cycles per second. Well, we're shaking the rope 25 times. That's our number of cycles. In 16.3 seconds, if we go ahead and do this math, 25 divided by 16.3, we get 1.53 hertz for our frequency. Plug that in to velocity is frequency times wavelength. So the frequency 1.53 and our wavelength of 19, we get 29.07. And now I know on the answer key we have 29.14. That's just a difference in rounding. Number 36, you repeat the sound lab. You use a 350 hertz tuning fork in a room that is 27 degrees Celsius. Calculate the length of tube that will allow you to create the first loud sound. Okay. Well, first, to do this, we are actually going to need our equation. Let me go ahead and grab this. Just grabbing our little equation slip that we're giving you. This one is given on our equation slip, so it's not something you need to add in. Here we are. We say that the speed of sound is 331.5 plus 0.6 times the temperature, T. A lot of people, so many people, will make the mistake of thinking this is multiplication. It is not multiplication. If you do that, you end up with huge speeds. Saying that the speed of sound is 4,000 meters per second. It is not. It never really will be. It's always going to be 300 something. No matter how cold it is, no matter how hot it is. Our temperature is 22 degrees Celsius times 0.6. So we get, if we continue on, right over here, this right term is 13.2 plus 331.5. We get 344.7 for the velocity of sound. Okay, now, why is this relevant? Well, we're dealing with a pipe. Let's draw in our pipe. One end is closed. There must be a node on the closed end. The other end is open. Our first sound pattern is going to look like this. Wow, my hands are shaky. This is a half of a loop, not a full loop. Where we just said one loop is half of a wavelength, this is half of a loop. This is a quarter of a wavelength. What this means, this length of pipe is a quarter of a wavelength. So if we can find out what a wavelength would be, given the frequency of the tuning fork, given the temperature in the room, then we know how long the pipe must be to make this first sound. So, again, velocity is frequency times wavelength. We want to solve for that wavelength. Velocity is 344.7. Frequency is 350. 344.7 divide by 350, we find that our wavelength is 0.98 meters. What does that mean for the length of the tube? Well, this is the length of the entire wave. We're fitting a fourth of the wave in there. So take our number, 0.98, and divide by 4. And we find the length only needs to be 0.245 meters. B, calculate the length required to create the second loud sound. Well, here, we're still working in a pipe. We still have the same rules. We need a node at our closed end, an antinode at our open end. So let's draw this in. Node here, what this pattern will look like. The second sound, remember, you cannot ever have a note here. This pattern is not going to resonate. It will not make a sound. What we need instead is a pattern that looks something like, and we'll get rid of this note here because that's not actually there. Something like this. We still have two nodes, but we do have two nodes now, as opposed to before. That first pattern, we only had one node. Now, if we split this up into quarters of a wavelength, we have 1/4 here, 1/4 here, and 1/4 here, because every half a loop is a quarter of a wavelength, just like we said for number 36, part A. This means this whole length of the pipe is, the length is 3/4 of a wavelength. Okay, now, we know the velocity, we know the frequency, solve for the wavelength, same thing we just did, 344.7, I don't really need to do this again, equals 350 times wavelength. We know the wavelength is 0.98 meters. Solve for the length. We can really use our equation, right? Length is 3/4 the wavelength. Plug in your wavelength, and then just flip our equation around, right? Really, this is the same thing as 4/3 the length is equal to wavelength. That'd be useful if we had the length of the pipe, but we don't. We can just plug in 0.98 times 3 divided by 4, and we get that the length should be 0.738 meters. Alright, number 37, use this physics classroom link to practice color. Make sure you know how color adds, how filters work, and how we see different colors in different types of light. If you open this up, again, you'll see the physics classroom. This concept builder is so great. I'd highly recommend you practice this. You should know your primary colors, how they add, how color filters work, everything. There's multiple different levels. Try the different levels. Make sure that you're comfortable with them. Number 38, explain why a leaf appears green to our eyes. Well, does the leaf just emit green light naturally? No. The reason it appears green is because sunlight, or really any white light, is the three primary colors combined. When our eyes see white, it's really red, blue, and green all combined together. Leaves appear green because they are reflecting green light to our eyes. So say we have, let's say that's a leaf, let's say it's green. The reason we see green is if we have our eye over here. This is our eye. If we have blue light coming in, red light, and green light coming in, again, that's just white light, combination of all our primary colors. The blue and red are absorbed, the green gets reflected, and that's what we see. State the law of reflection. Well, law of reflection is just that the angle of incidence is equal to the angle of reflection. Drawing an example, well, let's start off with a flat surface. Let's label our normal line right here. If we have light coming in at some angle, like so, it will bounce and leave at that same angle, just like this. So that our angle of incidence right here, this would be our angle of incidence, is equal to our angle of reflection. A 5-foot-tall person stands in front of a flat mirror. Describe the location, orientation, size, and type of image produced by the flat mirror. Okay. It's a flat mirror, so we know for our L, the location, right? The image, I'm going to talk through this. This is going to be a lot of words. For the location, it's going to be behind the mirror at an equal distance as the object from the mirror. So, if the person is standing 3 feet in front of the mirror, the location of the image would be 3 feet behind the mirror. It will be right side up. Since it's a flat mirror, that's the orientation. The size is that it will be 5 feet tall, same size as the object. And the type is that it will be a virtual image. Flat mirrors always create virtual images. Number 41. Draw a curved mirror and label the zones. Let's do it. We'll start out like this. Let's draw in our curved mirror. We can label, let's say our focus is right here. Then just eyeballing it as best we can. Here would be twice the focal length. Zone 1 is anything beyond 2F. Zone 2 is anything between 2F and F. Zone 3 is between F and the mirror. And then zone 4 is anything beyond the mirror, behind the mirror. Number 42, which zones of the curved mirror are in front of the concave mirror? Which zones are in front of the convex mirror? Well, zone 1, 2, and 3 are in front, as we can see right up here. Those are in front of the concave mirror. We say it's concave because it looks like a cave, right, as you're entering it. In front of the convex mirror is just zone 4. Describe the lost characteristics of the image when the object is located in zone 1. Well, the image will be in zone 2. It will be upside down. It will be smaller. And it will be real. If you're still working on your study buddy, I'd highly recommend you add in these lost characteristics. You can add in a little table of them, so you don't have to memorize them. Number 44. When an object is located at the focus, where is the image? This is a trick question. We're telling you, it's a trick question. If the object is at the focus, there will be no image. .45. Why is the flashlight bulb always placed at the focus of a concave mirror? This is because the light reflects parallel to the primary axis. So essentially, if we have, say we have our mirror, and this is our focus, right here. When we have light that is emitted from this focus in any possible direction, no matter what direction it's coming toward the mirror, since it came from the focus, it will always reflect parallel to that principal axis. So all of the light, instead of spreading out and you getting this weak light that spreads everywhere, you get this steady beam of light that goes forward forever. Refraction is just the bending of light when light changes medium. Number 47. In terms of refraction, what does fast mean? What does SOFA? Well, fast is going from fast to slow, bends towards. So that means if you're going from a fast medium to a slow medium, light bends towards the normal line. And then SOFA means if you are going from a slow medium to a fast medium, light is going to bend away from normal. Which has a faster speed of light, air or water? It is faster in air. Number 49, which has a larger index of refraction, air or water? Water. The larger index of refraction means that light travels slower. And number 50, calculate the refraction angle when light goes from water to air at an incident angle of 34 degrees. Use Snell's law and the correct index of refraction values from your notes. Okay, Snell's law, theta 1. Really, n sine theta 1. Let's move this together so it doesn't look so weird. Snell's law is n1 sine theta 1 is equal to n2 sine theta 2. These numbers just indicate the medium. So number 1 is the first medium, number 2 is the second medium, n is the index of our fraction. We're starting in water and going to air. So our first medium is water. Water has an index of refraction 1.33. It is coming in, that incident angle is 34 degrees. Then it ends up in air. Air has an index of refraction of 1. We're trying to find out this angle. To do this, what we're going to do, and we can demonstrate this on our calculator. Let's scroll on over. First, let's clear this. Let's make sure in our mode, make sure you're in degree mode. If you're in radians, you're going to get the wrong answer. Our angle, sine 34, gives us this ratio, multiplied by 1.33, 0.74. That's what we get on our left-hand side. This is just a number. Equals, well, we have our 1, that's going to drop out. So right away, we have 0.74 equals sine theta 2. How do we solve this? Well, take the inverse sine of 0.74, and that is going to give us the angle. So if we go ahead and we say inverse sine of 0.74, the angle is 47, almost 48 degrees. Let's go ahead, we'll round up. 48 degrees. There you have it. Make sure you're working on your study buddy. Make sure you have everything you need to know for the test. Good luck.